Welcome to today's BCBA exam prep series. In this lesson, we're diving into Section D, Experimental Design. This is one of the most important and most misunderstood sections of the exam. Why? Because it's not just about definitions. It's about logic. You are not being tested on whether you recognize a design. You're being tested on whether you understand how to prove a functional relation. In this section, you'll learn how to prove causation, not just correlation. Master the single case designs the exam actually tests. Avoid common internal validity traps. And analyze data the way the BCBA expects you to. If you want to stop guessing and start answering with confidence, this lesson is for you. To win Section D questions, you need a clear strategy. Step 1. Identify the independent variable and the dependent variable. If you confuse these, the entire question collapses. Step 2. Eliminate validity threats. The exam loves to sneak in history, maturation, or measurement problems. Step 3. Match the design to the question. Not every situation calls for a reversal design. Not every situation allows withdrawal. And Step 4. Use visual analysis. This exam is not about complex statistics. It's about seeing patterns in the data. Here's a critical exam tip. Most wrong answers use a real design, but apply it incorrectly. Here's the roadmap for what you need to master in Section D. First, we start with variables, independent and dependent. Then we move into internal and external validity. After that, we cover the logic and strengths of single-case designs. Next comes data interpretation, level, trend, and patterns. Then we'll look at the major design types, including reversal and multiple baseline. We'll also cover experimental analyses, comparative, component, and parametric. And finally, we'll focus on real-world application, choosing the right design and implementing it correctly. If you understand how these pieces connect, Section D becomes much easier. Let's start with the foundation, independent and dependent variables. The independent variable, or 4, is what you manipulate. It is the treatment, the condition, or the intervention. The dependent variable, or DV, is what you measure. It's the behavior, the outcome, the response. Here's the key relationship. When the 4 changes, the DV should change. If you cannot clearly identify what is being manipulated and what is being measured, then you do not have an experiment. You have a description. The exam tests this constantly. Strong experimental designs always start with clear variables. Your independent variable must be operationally defined. That means it must be specific, observable, and manipulable. Your dependent variable must be measurable. If you can't observe it, record it, and quantify it, it doesn't belong in an experiment. Another key rule: only change one independent variable at a time. Why? Because changing multiple variables destroys experimental control. Here's a very common trap on the exam. They'll describe a study that changes multiple things at once, and then ask if it proves causation. It doesn't. Now let's talk about validity. Internal validity asks, did the independent variable actually cause the change? External validity asks, can the results be generalized to other people, places, or situations? Single-case designs prioritize internal validity. Why? Because their main purpose is to demonstrate a functional relation, not generalization. You must prove cause and effect first. Generalization comes later. On the BCBA exam, internal validity is almost always more important than external validity. Internal validity is all about control. It asks one simple question: did the independent variable cause the change? To answer that, you must rule out alternative explanations. That means controlling confounding variables, anything else that could explain the behavior change. You also need to look at the timing of change. If the behavior changes before the 4 is introduced, that's a red flag. So remember, internal validity is about proving causation, not coincidence. Now let's talk about the most common threats to internal validity, and these show up constantly on the exam. First, history. This refers to outside events that happen at the same time as the intervention. For example, a school schedule change, a new teacher, or a major life event. Second, maturation. This is natural change over time. Skills often improve simply because of development, not because of treatment. Third, testing or practice effects. If a person improves simply because they're being measured repeatedly, that's not a treatment effect. Fourth, instrumentation changes. This happens when the way behavior is measured changes during the study. For example, observer drift, or changes in definitions. Here's your exam rule. Always ask, what else could explain this change? Let's apply these threats to real exam-style scenarios. If a new school schedule starts at the same time the behavior changes, that's a history threat. Timing matters. If behavior improves because the learner is naturally developing, that's maturation. If the behavior definition changes halfway through the study, that's instrumentation. The exam loves to hide these details in long scenarios. Your job is to catch them. Anytime the question asks, does this demonstrate a functional relation? Your brain should ask, could something else explain this? Single-case designs have 3 defining features. First, the individual serves as their own control. We compare their behavior across different phases. Second, repeated measurement. Data are collected continuously, not just once. Third, systematic manipulation of the independent variable. We intentionally change conditions to see what happens. This is what allows us to demonstrate experimental control. So instead of comparing groups, we compare phases. This is why you'll see sequences like ABA or ABAB. Single-case designs rely on a logical framework. First, prediction. Baseline allows us to predict what behavior would look like without intervention. Second, verification. When we introduce the intervention, we check whether behavior changes as expected. Third, replication. When we repeat the effect, we strengthen the causal claim. This logic is what proves a functional relation, not statistics, not averages. Logic. Let's compare single-case and group designs. In single-case designs, the individual is their own control. We focus on individual-level change. We use repeated measurement. We manipulate the independent variable systematically, and we look for functional relations. In group designs, the focus is very different. They use averages. They compare groups. They rely on statistical analysis, and they look for between-group differences. On the BCBA exam, you are almost always working within the logic of single-case designs. Single-case designs are powerful for several key reasons. First, high internal validity. This means we can confidently say that the intervention caused the behavior change. Second, they are sensitive to behavior change. We can detect even small shifts in behavior over time, especially with repeated measurements. Third, they are ethical and practical. These designs are individualized, meaning they cater to the unique needs of each client. And finally, they are resource efficient. You don't need a huge group of people to conduct these studies, which makes them ideal in real-world settings. For the BCBA exam, focus on the strengths of single-case designs. They are designed to prove causality. When you interpret single-case data, you need to focus on 4 elements. First, level. This refers to the value of the dependent variable at any given point, typically the baseline or treatment phase. Second, trend. Is the behavior going up, down, or remaining steady? You want to identify the direction of the behavior change. Third, variability. Look at how consistent the data points are. Is the behavior stable, or does it fluctuate a lot? Fourth, immediacy of effect. How quickly does the behavior change once the intervention is applied? A strong intervention shows a rapid shift. Exam tip. Always look for consistent patterns across all 4 elements. If the trend is unclear or variable, the design may not show a functional relation. In BCBA exams, visual analysis takes priority over statistics. What does that mean? It means you are looking for patterns in the data, not trying to perform complex calculations. A strong visual analysis shows a consistent pattern across phases, like baseline to treatment. A clear shift after introducing the independent variable, backed by multiple data points. A weak visual analysis focuses on one good data point and ignores the overall pattern. This can be a trick the exam uses to mislead you. Key visual analysis strategies. Always compare data across phases. Ignore single outlier data points. Focus on overall trends. Exam tip. The exam wants to see your ability to logically analyze data, not to crunch numbers. There are several types of single-case designs, each with its strengths. Reversal ABAB. This is the strongest design for demonstrating cause and effect. It involves alternating between baseline and treatment phases. However, it requires that the behavior be reversible, and it cannot be used when reversing behavior would be harmful. Multiple baseline. This design involves introducing the intervention at different times across behaviors, settings, or participants. It does not require withdrawal, making it more ethical than reversal designs. Multielement. This design allows for rapid comparison between different conditions. You don't need to withdraw the treatment, and it works well when you want to compare multiple interventions at once. Changing criterion. This design gradually shifts the goal or criterion for behavior change. It's great for behaviors that need step-by-step improvement. Remember, each design serves different needs depending on the behavior and the intervention. Let's dive deeper into the reversal design, ABAB. This is one of the most powerful designs for proving cause and effect relationships. You alternate between baseline, A, and treatment, B, phases. If the behavior changes when you introduce the treatment and then returns to baseline when treatment is withdrawn, that's strong evidence that the treatment caused the change. However, ethical limitations arise if the behavior cannot be safely reversed. For example, if you're studying self-injurious behavior, you cannot ethically reverse that behavior, so this design would not be appropriate. Exam tip: make sure you are always considering the ethical implications of using a reversal design in your answers. The multiple baseline design is often considered the ethical alternative to the reversal design. This design is great because it doesn't require withdrawing the treatment. You apply the treatment at different times across behaviors, different target behaviors of the same individual. Settings: the same behavior, but in different environments. Participants: the same behavior across different individuals. The staggered start across different conditions gives you control over the data, while still respecting the client's needs and safety. This design is especially useful when it's not possible or ethical to remove the intervention. Let's take a closer look at two more important designs. First, the multi-element design. This design allows you to rapidly compare different conditions or treatments without withdrawing any interventions. It requires that the conditions be easily discriminable, meaning they must be distinct enough for the participant to understand which treatment they are receiving at any given time. Next, the changing criterion design. This design is used when the goal is to gradually change behavior over time. You establish a series of gradually increasing goals or criteria for the behavior you want to change. It's an effective method for shaping behavior, where the target behavior is modified step by step. Both designs are valuable in specific situations. The key takeaway is, know when each design is appropriate. Now, let's talk about the different types of experimental analyses. Comparative analysis. This type of analysis compares two or more treatment conditions to determine which one is more effective. It helps to identify which treatment produces the greatest change. Component analysis. This is used to break down an intervention into its individual elements. By doing this, you can determine which component of the intervention is the most effective. Parametric analysis. This looks at the relationship between the dosage or intensity of the treatment and the behavior change. It helps identify the optimal level of the intervention needed to produce the desired effect. Let's look at some exam-style scenarios for each type of analysis. First, comparative analysis. Scenario: you're comparing intervention A with intervention B. The goal is to determine which intervention is more effective for reducing a specific behavior. This is a typical between-subjects comparison, where random assignment may be used. Second, component analysis. Scenario: you're studying the effects of a behavioral intervention with several components, such as reinforcement, punishment, and instruction. You isolate the components and see which one contributes most to the behavior change. This allows you to identify the active ingredients of the treatment. Finally, parametric analysis. Scenario: you want to understand the relationship between the intensity of a behavior modification program and the degree of behavior change. This is when you examine the dosage effect to find the most effective level of intervention. When applying single-case designs in real-world settings, there are a few key things to keep in mind. Match the design to the behavior. For simple behaviors, a reversal design might work best. For more complex behaviors, consider using a multiple baseline design. Consider ethics first. Always prioritize the client's safety, well-being, and rights. Choose the design that will not only yield the best results, but is also the most ethical. Ensure control is possible. Before starting the intervention, make sure the baseline is stable and the intervention is clearly defined. You need to have a clear idea of how to withdraw the treatment or adjust if necessary. Remember, assess, design, and then apply the intervention. Let's look at some common patterns in the exam to help you select the right design. Cannot withdraw. If you cannot withdraw the treatment for ethical reasons, multiple baseline designs are often the answer. This is common for behaviors where withdrawal could cause harm. Compare treatments. If the question asks you to compare two or more interventions, the multi-element design is often the best choice. It allows for rapid comparisons between conditions without the need to withdraw treatment. Gradual goals. If the question involves gradually increasing the target behavior, a changing criterion design is what you're looking for. This is perfect for cases where behavior must improve step by step. Choosing the right design is often the main point of the exam question. Now, let's talk about some common Section D traps. Correlation versus causation. One of the biggest traps in experimental design is confusing correlation with causation. Remember, correlation does not equal causation. Your job is to prove a functional relation, not just an association. Ignoring validity threats. A lot of questions try to trick you by presenting validity threats, like history, maturation, or practice effects. Ask yourself, what else could explain this change? Unethical design choices. The exam may present a design choice that's the strongest method, but could be unethical. Always prioritize the ethical considerations of your design. Ethics must come before design strength. Let's wrap up Section D with some final takeaways. First, experimental design equals proof. Your goal in experimental design is to prove a functional relation, not just show a correlation. Control equals credibility. The more control you have over the experiment, the stronger your claim that the intervention caused the behavior change. Second, design choice matters. Make sure you select the right design based on the behavior and the clinical question you're addressing. Don't just choose the strongest design. Think about what's ethical, feasible, and appropriate for the situation. Finally, visual analysis drives decisions. The exam isn't about math, it's about logic. Focus on the patterns in the data, not the complex statistics. Visual logic is key. Look for clear trends and trust your eyes. Final checklist. Identify variables. Eliminate threats. Select the right design. Perform visual analysis. And, most importantly, practice BCBA-style questions.